All right, let's look at another torque situation here. So this is an Atwood machine. It's a situation you should be fairly familiar with at this point. So our focus is more on the pulley here. We're given that this pulley has some radius r, and moment of inertia I. So those are given about the pulley. We're given the masses of the two blocks here, and we're told we can assume the system's released from rest. We're asked to determine the speed of the blocks after block 1 has descended through distance d. So that tells us something about the behavior of the system. Let's just say, all right, it's going to descend through some distance d, and I want to know how fast the blocks are going at that point. Cool. So this is a problem that, again, you've done before the pulley was allowed to have mass, and now obviously the pulley does have mass, so that changes things. So we need to consider torque here as well. The first thing for us to do, though, is draw our free body diagrams and torque diagram. So we'll have 3 diagrams in total here. We'll have a free body diagram for block 1. We'll have a free body diagram for block 2. And then we'll have a torque diagram for the pulley. And each one of these are analytical diagrams, remember. So each one of these diagrams is going to render us at least one equation. I think we'll just get one due to the simplicity of this problem, one equation from each diagram, and then we'll use those to solve for what we want to solve for. So if I look at M1, again, we should be pretty good at doing these kind of free body diagrams at this point. M1, I know that I have weight directed downward, and I have tension upward. And block 2, I know I have weight directed downward and tension upward. Okay, now hang on a second. We've always said that the tension in a cord on either side of the pulley, like before this, we've always said that that tension is the same, that pulleys haven't changed the tension because we've been dealing with massless pulleys. But like, guess what? Now those like nice days are over. Now you have to deal with pulleys that have mass. So this is just more like the real world, right? So what this means then is that the tensions on either side of the pulley, whenever you have a dynamic situation, and that means a situation where alpha is non-zero, then the tensions are not the same. So now I need to subscript my tension. So I'm going to call the tension for block 1 T1 and the tension for block 2 T2. If you're thinking, if you think about this, like, why do the tensions all of a sudden have to be different? You can consider the fact that there has to be a net torque on the pulley to make it accelerate. I'm going to say that again. There has to be a net torque on the pulley to make it accelerate. If those tensions were the same, the net torque on the pulley would be 0 and it would not accelerate. All right, that's why before we had to always say our pulleys were massless, right? So that they didn't have any inertia, they didn't have any resistance to acceleration because we were just assuming that that there would be basically no torque on that pulley, that it would spin without torque. But now we're ready to think about things more like in the real world. All right, I'm going to throw a sign convention on here. I'll get ready for my torque diagram. I'll just draw the pulley in there. I'll go positive in the direction of acceleration. So we're told release from rest and M1 descends a distance d. That's telling us about the behavior of this situation. So I'm going to say downward is positive for block 1 and then upward is positive for block 2, as block 2 will be accelerating upward. So if block 1 is accelerating downward, block 2 is accelerating upward, what's the direction of alpha? So look at it, right-hand rule. So that means that alpha is going to be out of the page, right? So I'm going to make out of the page, that's my notation for out of the page, I'm going to make out of the page positive for the pulley. Really important to have a sign convention. Torques are vectors, you guys. So be sure you have a sign convention here. All right, so let's now think about what are the forces that are acting on the pulley so I can figure out my torques. So if I look at the pulley, I can see that, well, I've got this tension 1 on the left-hand side pulling down, and I've got tension 2 on the right-hand side pulling down. Okay. So remember, like we realize there's an axle that's supporting the pulley here. So we're not worrying about the whole pulley falling down. We're not worrying about what the center of mass of the pulley is doing. As far as the center of mass is going, the pulley is in equilibrium, but it's not in static equilibrium, right? It's in equilibrium such that its center of mass is not accelerating, but it is rotating. Yeah. So it is a type of equilibrium that we can call it equilibrium. It's just not static equilibrium. Static equilibrium is where a body has no rotation and no translation. Okay. So these are our two tensions. In order to do a torque diagram, we also need to fill in the R values. And notice that these R's are two different R's. Sometimes students miss this. So I'm going to call this R sub 1 and R sub 2. So those R's have the same magnitude, right? We're given the radius of this pulley is big R. I get it. They have the same magnitude. It doesn't mean they're the same vector. These are vector quantities. They point in different directions. So technically, these are different quantities, okay? Good news, though, they're each at a right angle with respect to the tension that they're relevant to. So that makes our math kind of cool. All right, let's go ahead and apply second law. So if I'm looking at, I'll go through these one at a time. So looking at going to block M1, what do I have here? M1G minus T1 equals M1A. There we go. And block 2, now I have upward positive T2 minus M2G equals M2A. Now these two accelerations are the same. These blocks move together, right? Just as they always have. You've seen these situations before. So those are the two equations I render second law on the free body diagrams. Now I get an equation for my pulley diagram. So that's cool. My torque, I'm going to figure out my torques first, though, okay? So I'll figure out what I'm going to call torque 1 here, and that's going to be R1 crossed in with T1. All right, so I want you to just conceptualize that. So torque 1, that's going to give me magnitude of R1, magnitude of T1, times sine of 90 degrees. They're 90 degrees apart. And what's the direction there? So right-hand rule, crossing R1 into T1, that gives me out of the page there. So torque 1, I can write this a little more simply here, is going to be equal to R, magnitude of R1 is big R, that's given, times T1, we can't express that yet, out of the page. Sine of 90 degrees is what? Okay, so that's torque 1. Now let's figure out torque 2. That's going to be the vector product of R2 crossed into T2. I just really don't want you to forget that what you're doing is a vector operation here. Torque 2 equals magnitude of R2. So notice that I dropped the hat here, right? I'm representing magnitude. So when you use hats, we use them intentionally. Magnitude of T2 times sine of 90 degrees again. And now let's use right-hand rule to find the direction. R2 crossed in with T2, that's going to be into the page. All right, so one of the reasons that I have a hat on this torque 2 in this expression is that I know I'm going to add a direction onto there. So, and you just use in or out of the page as your directions there, that's fine. So torque 2 is equal to magnitude of R2, which is given to us as big R in this problem, magnitude of T2, sine of 90 is 1, and that is into the page. So into the page, notice that's my negative direction, right? So actually, I'm going to go back and make sure it's more visible. My negative sign, RT2, and I know that that's an into the page, right? So it might seem like, oh, she's putting all this notation on there. She's got the end of the page and the negative sign. I would say that like you really want to remind yourself of this because this is, it might be the first time you're working within the in and out of the page axis, right? With that third dimension. So your brain needs like a little extra reminding about what to do. So I've got these two torques. I'm going to continue work on the left-hand side of the page where I have a little bit more space here. Um, what I know is that I can relate the sum of the torques on my pulley through Newton's second law. I can relate the sum of the torques to the product of I and alpha. So that's what I'm going to do right now. So I'll have, what that will look like for me is torque 1 minus torque 2. Notice the hats are off here, right? So I'm talking about the magnitudes there. Torque 1 minus torque 2 is equal to I, which is a given in this problem, multiplied by alpha. So remember the relationship between A and alpha. A equals alpha times R. So that tells us, what is alpha? Alpha is equal to A over R. So I can just write it like that. All right. So this will flesh out into a little bit more detailed equation as I sub in from what I figured out for my torques. So what this is going to look like is RT1 minus RT2 equals IA over, oh, and this is big R, this radius here, because it's given to us as a big R. So we got to use the right notation. All right, so this is my third equation. So, doing the torque equation stuff is probably just going to take a few more moves, obviously, than the second law stuff just for the translation. But you've got the translation down. Like that should have been fairly trivial part of this problem. So really the new content and the part of the problem to spend a little more time on and really make sure you're getting it right, of course, is make sure you keep track of the torque stuff. So I have three equations, three unknowns. It's time, right, for algebra intermission. Pick what your favorite method here is to use. And then you're also going to need to use a little kinematics here, right? Because notice that you're being asked to find the speed of the blocks. So say, you're going to use some algebra and then you're going to solve for acceleration. So you can solve for acceleration, obviously, using these three equations that I have boxed up here. Those are the three equations from your three diagrams. And once you solve for acceleration, now you can determine, you've got the kinematics to do this. You can determine the final speed. Determine the VF. Good. Okay. So details and the written solutions. A lot of this problem is review, right? I mean, the force stuff, the kinematic stuff. So that's just kind of integrating this new piece in, which is torque.